Welcome to our YouTube channel Experience Tutor. Today we'll discuss Class 11th Physics, Work, Energy and Power, Chapter 6, NCERT Solution, Part 3. Our mission is to provide free classes on YouTube for all students of Class 6 to Class 12 and the students who are preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we start today's class, we have a small request. Please subscribe, like and share our channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's class. In the last class, we have completed till the problem number 6.21. In today's class, we'll start with 6.22. A person trying to lose weight due to lift a 10 kg mass 1000 times to a height of 0.5 meter each time. Assume that the potential energy lost each time C lower the mass is dissipated. A. How much work does C do against the gravitational force? B. Fat supplies 3.8 multiplied by 10 to the power 7 joule of energy per kilogram, which is converted to mechanical energy with a 20% efficiency rate. How much fat will be later used up? So let us see the solution. Mass of the weight m is equal to 10 kg, height to which a person lifts the weight h is equal to zero point 0.5 meter. Number of times the weight is lifted n is equal to 1000. Work done against gravitational force n multiplied by mgh. So putting the values of n, m, g and h, we get 1000 multiplied by 10 multiplied by 9.8 multiplied by 0.5. Upon multiplying, we get 49 multiplied by 10 to the power 3 joule, that is 49 kilojoule. Energy equivalent to 1 kg of fat is equal to 3.8 multiplied by 10 to the power 7 joule. Efficiency rate is equal to 20%. Mechanical energy supplied by the person's body, that is 20%, that is 20 upon 100 multiplied by 3.8 multiplied by 10 to the power 7 joule is equal to 1 upon 5 multiplied by 3.8 multiplied by 10 to the power 7 joule. Equivalent mass of fat lost by the data is equal to 1 upon 5 multiplied by 3.8 multiplied by 10 to the power 7 multiplied by 49.49 multiplied by 10 to the power 3 is equal to 245 upon 3.8 multiplied by 10 to the power minus 4 is equal to 6.45 multiplied by 10 to the power minus 3 kg. Let us see the next problem. Our next problem is 6.23. A family uses 8 kilowatt of power. A direct solar energy is incident on the horizontal surface at an average rate of 200 watt per square meter. If 20% of this energy can be converted to useful electric energy, how large an area is needed to supply 8 kilowatt? B. Compare the area to that of the roof of a typical house. Let us see the solution. The answer is 200 meters square, but we have to understand how we get this answer. So power used by the family P is equal to 8 kilowatt, that is 8 into multiply by 10 to the power 3 watt. Solar energy received per square meter, that is 200 watt. Efficiency of conservation or conversion of solar energy to electric energy is 20%. Area required to generate the desired electricity is equal to capital A. As per the information given in the question, we have 8 multiplied by 10 to the power 3 is equal to 20% of A multiplied by 200 is equal to 20 upon 100 multiplied by A multiplied by 200, 200. So we can write 20 upon 100 multiplied by A multiplied by 200. So A is equal to 8 multiplied by 10 to the power 3 upon 40. That is equal to 200 meters square. The area of the solar plate required to generate 8 kilowatt of electricity is almost equivalent to the area of the roof of the building having a dimension 14 meter into 14 meter. So 14 meter into 14 meter is 196 meter square, which is approximately equal to 200 meter square area, and this is the answer. So let us move to the next question. The next question is from additional exercise, that is 6.24. A bullet of mass 0.012 kg and horizontal speed 70 meter per second strikes a block of wood of mass zero point 0.4 kg and instantly comes to rest with respect to the block. The block is suspended from the ceiling by means of thin wires. Calculate the height of which the block rises. Also, estimate the amount of heat produced in the block. So, the solution is mass of the bullet small m is equal to 0.012 kg. Initial speed of the bullet UB is equal to 70 meter per second. Mass of the wooden block capital M is equal to zero point 0.4 kg. Initial speed of the bullet wooden block U capital B is equal to 0. Final speed of the system of bullet and the block is equal to V. Applying the law of conservation of momentum, M U small b is equal to capital M U capital B is equal to M small m plus capital M V. So putting the values of M U B M capital M U B U capital B and V, we get 0.012 multiplied by 70 plus zero point 0.4 multiplied by 0 is equal to 0.012 plus zero point 0.4 multiplied by V. So V is equal to 0.84 upon 0.412, which is equal to 2.04 meter per second. Now, for the system of the bullet and the wooden block, we have mass of the system m dash is equal to 0.412 kg. Velocity of the system is equal to 2.04 meter per second. Height up to which the system rises is equal to h. Applying the law of conservation of energy to this system, potential energy at the highest point is equal to kinetic energy at the lowest point. That is m dash gh is equal to half m dash v square. H is equal to half v square upon g is equal to half 2.04 whole square upon 9.8 is equal to 0.2123 meter. The wooden block will rise to a height of 0.2123 meter. Heat produced is equal to kinetic energy of the bullet minus kinetic energy of the system is equal to half m u square minus half m dash v square is equal to half 0.012 multiplied by 70 square minus half multiplied by 0.412 multiplied by 2.04 square is equal to 29.4 minus 0.857, which is equal to 28.54 joule. Let us see the next problem. So now we'll see the problem number 6.25. Two inclined frictionless tracks, one gradual and other steep, meet at A from where two stones are allowed to slide down from rest, one on each track. Figure 6.16. Will the stone reach the bottom at the same time? Will they reach there with the same speed? Explain theta 1. Explain. Given theta 1 is equal to 30 degree, theta 2 is equal to 60 degree, h height is equal to 10 meter. What are the speeds and time taken by the two stones? Let us see the solution. Answer is no. They will not reach at the same time. The stone moving downward, the stone moving down to the steep plane will reach bottom first. So yes, next answer is yes, the stone will reach the bottom with the same speed, that is VB is equal to BC is equal to 14 meter per second. Time will be T1 is equal to 286 second, T2 is equal to 1.65 second. Now let us see the free diagram for the given problem. So here we can see the weight is acting in the left hand side, that is in triangle ABD. We can see the weight mg is acting vertically downward. So mg can be drawn into vertical and horizontal components, that is mg cos theta 1 and mg sin theta 1, where mg sin theta 1 is the horizontal component and mg cos theta 1 is the vertical component, which equivalents the force, the reaction force R1. Similarly, in triangle ADC, if we draw the freehand diagram for the forces, then we can see mg, which is acting vertically downward, and we can draw the vertical and horizontal components for mg, that is mg sin theta 2 is the horizontal component and mg cos theta 2 is the vertical component, which equivalents or which evaluate the reaction R2. The height is h. Now here the initial height AD for both the stones is the same, that is h. Hence both will have the same potential energy at point A. As per the law of conservation of energy, the kinetic energy of the stone at B and C will be same. That is half mv1 square is equal to half mv2 square. That is v1 is equal to v2 is equal to v. Let us consider it is as v. So where m is the mass of each stone, v is the speed of the stone at the point B and C. Hence, both the stone will reach to the bottom with the same speed, that is v. For stone 1, net force acting on the stone is given by F net is equal to MA1 is equal to mg sine theta 1. A is equal to g sine theta 1. For stone 2, A2 is equal to g sine theta 2. Since theta 2 is greater than theta 1, therefore sine theta 2 will be greater than sine theta 1. Using the first equation of motion, the time of slide can be obtained as v is equal to u plus at, t is equal, where u is equal to 0 and t is equal to v by a. For stone 1, t1 is equal to v by a1. For stone 2, T2 is equal to V by A2. A2 is greater than A1. Therefore, T2 will be smaller than T1. Hence, the stone moving down the steep plane will reach the bottom first. The speed v of each stone at point B and C is given by the relation obtained from the law of conservation of energy. mgh is equal to half mv square, v is equal to under root 2 gh. Putting the values of g and h, we get 2 multiplied by 9.8 multiplied by 10, that is under root 196 is equal to 14 meter per second. The time are given as t1 is equal to v by a, that is v by g sine theta 1, that is 14 by 9.8 multiplied by sine 30, that is 14 by 9.8 multiplied by half, that is 2.86 seconds. T2 is equal to V by A2, that is V by G sine theta 2 is equal to 14 by 9.8 multiplied by sine 60 degree is equal to 14 by 9.8 multiplied by 3 by 2 root 3 by 2 is equal to 1.65 seconds. Now let us see problem number 6.26. A 1 kg block situated on a rough incline in connected to a spring of spring constant 100 Newton per meter as shown in the figure 6.17. The block is released from rest with the spring in the unstretched position. The block moves 10 centimeter down the incline before coming to rest. Find the coefficient of friction between the block and the incline. Assume that the spring has a negligible mass and pulley is frictionless. Let us see the solution. Mass of the block m is equal to 1 kg. Spring constant k is equal to 100 Newton per meter. Displacement of the block x is equal to 10 centimeter, that is equal to 0.1 meter at equilibrium. So in the freehand diagram, we can see mg is the force acting downward, which can be drawn into vertical and horizontal component. The horizontal component is mg sine 37 degree, and the vertical component is equal to mg cos 37 degree, which is the equivalent the reaction force R. Now at equilibrium, normal reaction R is equal to mg cos 37 degree. Frictional force F is equal to mu R, that is mg sine theta sine 37 degree, where mu is the coefficient of friction. Net force acting on the block is equal to mg sine 37 degree minus m. That is mg sine 37 degree is equal to mg sine 37 degree minus f. And putting the value of f, we get mg sine 37 degree is minus mu mg cos 37 degree. At equilibrium, the work done by the block is equal to the potential energy of the spring. Mg bracket sine 37 degree minus mu cos 37 degree bracket close multiplied by x is equal to half kx square, which is putting the values of mg, then we get 1 multiplied by 9.8 multiplied by in bracket sine 37 minus mu cos 37 is equal to half kx is equal to half. Putting the value of k and x, we get 100 multiplied by 0.1. Again, we get 0.602 minus mu multiplied by 0.799 is equal to 0.510. Mu is equal to 0.092 upon 0.799 is equal to 0.115. Now let us see the next problem, that is 6.27. A volt of mass 0.3 kg falls from the ceiling of an elevator moving down with an uniform speed 7 meter per second. It hits the floor of the elevator. Length of the elevator is 3 meter and goes and does not rebound. What is the heat produced by the impact? Would your answer be different if the elevator was stationary? Let us see the solution. Mass of the volt m is equal to 0.3 kg. Speed of the elevator 7 meter per second. Height h is equal to 3 meter. Since the relative velocity of the volt with respect to the lift is zero, at the time of impact, potential energy gets converted into heat energy. Heat produced is equal to loss of potential energy, that is mgh. Putting the value of mg and h, we get 0.3 multiplied by 9.8 multiplied by 3, that is equal to 8.82 joule. The heat produced will remain the same even if the lift is stationary. This is because of the fact the relative velocity of the volt with respect to the lift remains zero. Let us see the next problem, that is 6.28. A trolley of mass 200 kg moves with a uniform speed of 36 km per hour on a frictional track. A child of mass 20 kg runs on a trolley from one end to the other, that is 10 meter away, with the speed of 4 meter per second relative to the trolley in the direction opposite to the to its motion, and jumps out of the trolley. What is the final speed of the trolley? How much has the trolley moved from the time the child began to run? Let us see the solution. Mass of the trolley capital M is equal to 200 kg. Speed of the trolley v is equal to 36 km per hour, that is 10 meter per second. Mass of the boy small m is equal to 20 kg. Initial momentum of the system of the boy and trolley is equal to capital M plus m bracket close v. So putting the value of capital M, small m and v, we get 200 plus 20 plus multiply by 10, that is 200 to 2200 kg meter per second. Let v dash be the final velocity of the trolley with respect to the ground. Final velocity of the boy with respect to the ground is v dash minus 4. Final momentum capital M v dash plus small m v dash minus 4. Putting the value of capital N and small m and v dash capital M and small m, we get 200 v dash plus 20 v dash is equal to 80. That is 220 v dash minus 80. As per the law of conservation of momentum, initial momentum is equal to final momentum. That is 2200 is equal to 220 v dash minus 80. Putting the values, solving the values for v dash is equal to 2280 upon 20 to 220, that is 10.36 meter per second. Length of the trolley is equal to L is equal to 10 meter. Speed of the boy v double dash is equal to 4 meter per second. Time taken by the boy to run t is equal to 10 by 4, that is 2.5 seconds. Distance moved by the trolley v double dash multiplied by t, that is 10.36 multiplied by 2.5, that is 25.9 meter. The next problem is 6.29. Which of the following potential energy curves in figure 6.18 cannot possibly describe the elastic collision of two billiard balls? Here r is the distance between the center of the balls. So you can see the six figures in figure 6.18. Now let us see the solution. So answer is 1, 2, 3, 4 and 6. How we come with this answer? Let us see. The potential energy of the system of two masses is inversely proportional to the separation between them. In the given case, the potential energy of the system of the two balls will decrease as they come closer to each other. It will become 0, that is potential energy Vr is equal to 0 when the two balls will touch each other. That is at r is equal to 2r, where r is the radius of the each billiard balls. The potential energy curves becomes given in the figure 1, 2, 3, 4 and 6 do not satisfy these two conditions. Hence, they do not describe the elastic collision between them. And now let us see the next problem. Now problem number 6.30. Consider the decay of free neutron at rest. Neutron gives proton plus electron. Show that the two body decay of this type must necessarily give an electron of fixed energy and therefore cannot account for the observed continuous energy distribution in the beta decay of a neutron or nucleus. So in figure 6.19 we can see x-axis as kinetic energy of beta particle emitted, and y-axis we can see number of beta particles per unit energy interval. Note the simple result of this exercise was one among the several arguments advanced by W. Pulley to predict the existence of third particle in the decay products of beta decay. This particle is known as neutrino. On we now know that it is a particle intrinsic spin half like E minus P or N, but in natural what is natural and either massless or having extremely small mass compared to the mass of electron, and which interacts very weakly with matter. The correct decay process of neutron is n is equal to p plus e plus frequency nu. Let us see the solution. The decay process of free electron neutron at rest is given by neutron is equal to proton plus uh, 1 electron. From Einstein's mass energy relation, we have the energy of electron is equal to as delta mc square, where delta m is equal to mass defect is equal to mass of neutron minus mass of proton plus mass of electron. C is speed of the light. Delta m and c are constant, hence the given two body decayed in uh, is unable to explain with continuous energy distribution in the beta decay of neutron or a nucleus. The presence of neutrino on LHS of the decay correctly explained the continuous energy distribution. And this is the end of this chapter. Before we close, we have a small request. Please subscribe, like, and share our channel with your friends and relatives. Please click on the subscribe button to support us, and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for watching our videos and supporting us.